sympathetic to many different dimensions from this lecture series, then something has gone badly wrong. So I absolutely dispute that this is making students more sympathetic to many dimensions. The rest may be guilty as charged. The plan today, survey. I'm going to recall Khovanov homology and then extend this slightly to define Rasmussen's S invariant, then talk about some, why we know there's some knots from what we've proved so far that are topologically sliced but not smoothly sliced, and then prove that that implies there's some exotic smooth structures on R4. This argument goes back to at least the 80s. There weren't really tools to know it worked earlier than that, but maybe the ideas were sort of around even before that. So I'm not quite sure who to attribute this argument to. Maybe Gompf. The parts 1 and 2, I'm going to leave out a bunch of details, and one thing we could possibly do in later lectures, the next lecture or two after this, is fill in some of those details, the ones that come out nicely and are sort of interesting, and skip the ones that are a little bit fiddly, or we can just move on. So the survey asks about, do you want more details of this, or do you want to move on in one of two directions? Questions? I mean, there's been no math yet, I acknowledge. Everybody ready? Oh, I have a bit of a headache, so if it's even more unclear than usual and lower energy, as you can tell it will be, I apologize. So recall. How did we build Khovanov homology? We started with this ring. I called it A, which was Z adjoint X mod X squared. It's a ring, so that means it's got a multiplication from A tensor A to A. And I also defined a co-multiplication from A to A tensor A, which was given by the coproduct of 1 is 1 tensor X plus X tensor 1, and the coproduct of X is X tensor X. Now, if we have a crossing, there are two ways you can resolve that crossing. It changes the knot, but it's a local change that gives you a new knot. This is the 0 resolution. This is not the 0 resolution. It's going great. Let's change the crossing. How about that one? This is the 0 resolution. Yes, this is the 1 resolution. And so now if you have a whole knot, my model example is always this 2 crossing unknot because it illustrates what's going on nicely. So if you have a knot, you can apply either resolution to each crossing, and you get a cube of resolutions. The dimension is the number of crossings. So this is the 0, 0 resolution. The 1, 0 resolution is just a single bean. The 0, 1 resolution is 3 circles. And the 1, 1 resolution is 2 circles, but facing the other way. And each edge, either 2 circles merge or 1 circle splits into 2. So we're now going to turn circles are going to turn into copies of A. Disjoint union is going to turn into tensor product. Merge is going to turn into multiplication. And split, maybe I'll write merge so it doesn't look stupid. And split is going to turn into delta, co-multiplication. So if we do that here, this turns into a commutative square, A tensor A tensor A tensor A tensor A, split, merge. Vertically here, nothing and a merge, and horizontally here, a split and nothing. This commutes. There's a standard way of putting signs on the edges so it anti-commutes, and in this picture you just put a minus sign on that edge. Any systematic way of putting signs on edges to make it anti-commute gives the same answer, so not focusing so much. Then I take the direct sum on each diagonal line, direct sum, direct sum, direct sum. So what does that look like? That's A tensor A plus A tensor A tensor A tensor A. What are these? This is the vectors with constant sum. This has sum 0. This has sum 1. 0 plus 1 is 1. 1 plus 0 is 1. This has sum 2. Okay, so that's the vertices getting added up, the ones that have the same sum. Okay, and what are the maps? Well, you just take the evident maps from a direct sum to a from the direct sum to the direct sum come from adding up these maps. So here, A goes to A tensor A by the coproduct, and A tensor A goes to A tensor A from id tensor M. A map from something plus something else is a row vector, in this case, a rows by columns, 1 by 2 matrix. And here, it'll be a 2 by 1 matrix given by, so to A we're multiplying, and here we were doing delta tensor id. This is a chain complex. You can extend it by 0. That's more comfortable. And then, so this complex is the Khovanov complex, and its homology is the Khovanov homology of K. And then the theorem was that this is an invariant. And the gradings are going, so this has 2 gradings. One up to an overall shift is just how far along you are in the complex. That's simple. I'm not going to write that down. There's a shift by like the number of negative crossings. The other one is going to play an extremely central role in the talk in ways that are going to be somewhat non-transparent, so I won't actually do any computations. But let me give you the formula for it just so you remember and it doesn't seem mysterious. So the quantum grading, that's the second one, is the number of crossings minus 3 times the number of negative crossings plus the height of the vertex, that was this sum from over there, plus the number of x's minus the number of 1's. Fine. And now I won't actually use that formula ever again in the talk. But I didn't want it, the grading is going to get used, so I didn't want to be mysterious. I am about to erase this. I should say I'm working on a book on Khovanov homology with Jake Rasmussen and Shuchit Sharkar. I probably shouldn't have said that on recording in case it never gets finished, but there are a few hundred pages written already, so hopefully something will get finished. And so the whole lecture series is informed by discussions with them and things they've explained to me, but today maybe even more than most, so I thought I would credit them for the help on saying things nicely, or hopefully nicely. Okay. We can maybe remove the quote. I'll leave the URL. So I want to change this slightly. So I'm going to replace A by a slightly different ring, by which I mean Frobenius ring with a co-multiplication, which I'm going to call AH. And this is Z adjoin XH mod x squared minus XH. So before x squared to 0, now x squares to XH. I'm going to think of this as being actually an algebra over Z adjoin H. So everything's going to commute with multiplication by H. And so I still have to just tell you what the coproduct of 1 and the coproduct of x are. And it's almost the same, 1 tensor x plus x tensor 1, but now minus h times 1 tensor 1. So this is a new term. And delta of x is just x tensor x. And now you just plug this into the Khovanov cube construction. And everything works the same. And everything works. Still works. And the same proof that I didn't say anything about implies it's a not invariant, gives that the chain homotopy type of CKH, I'll call it CKHH, just to remember I'm over this other thing, is a not invariant. And now I thought I better at least tell you what an example looks like. So this is for the trefoil, T23, the positive trefoil, I hope. This is not the Khovanov homology. This is a simplified version of the Khovanov chain complex, where I've simplified as much as possible without making it no longer chain homotopy equivalent. To get the Khovanov homology, there's still one differential left. It's here. So the Khovanov homology would have a 0 there, and the co-kernel of this is just a z mod 2 there. So Khovanov homology, you place this by 0 and that by z mod 2, and it's the same. Okay? But you sort of lose a little information doing that. Here, this is CKHH, and R is this ring Z adjoin XH mod X squared minus XH. And this arrow here means that the element 1 in R is mapping to 2x plus h here. Okay. The algebra got a little bit more complicated, so it's a little bit harder to understand the complex. If you like, you have your hands on it. This, z, we're pretty good at like some z's platted down in the plane, even a z mod 2. If I take this AH and I set h equals 0, then I get back to A, which was under here. Ta-da. Here. Okay, if I set h equals 0, x squared minus x squared, that's the same. If I set h equal to 0, then that extra term goes away. It's the same. Okay? So these should be related by also setting h equals 0. So CKH h of k with h set to 0 is just CKH. Okay. What? It doesn't look at all true. Well, you see, R, if I take Z adjoin XH, this was R mod x squared minus XH. What does that look like, actually? Maybe I'll draw just the z's. So I've got a z, 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 and I'm detoured. I shouldn't be doing this, but OK. H looks like that. X looks like that. And now X or H takes me there, and X takes me there. So dot, dot, dot. This is sort of how you should think about this ring. Okay? There's a Z adjoin H here, and there's a Z adjoin H here. And they differ by multiplication by x. And once you multiply by x, then x just weirdly walks you up that tower. So x takes you from this tower to that one, and then walks you up. And so when I quotient by h, all this crud goes away. And I'm just left with these two z's. So those are the two z's that come from this R. It splits into those two z's. And this splits into those two z's. And if you track through what I wrote there, this is that multiplication by 2. OK. Did I want to say something more about that? So I guess exercise. The picture on the right turns into the picture on the left. Maybe I didn't want to say more about that. Onwards. Questions so far? Yeah. That's what I wanted to say. Thank you. I knew there was something I wanted to say. The grading of x is 2, and that's also the grading of h. Good. If you look at, say, this term, it looks like it has the wrong number of x's in it, and the h is somehow compensating, and the grading of h compensates for the grading of, for the grading of x. So this is a graded ring, not just a ring. Good. Thank you. That was exactly what I was forgetting to say. And that's why these two z's end up in different. You're right. These z's came from this R. 1 is in the grading this, but x is in grading this, because x had grading, quantum grading 2. So that's why it's split also vertically. Perfect. OK. Theorem. OK, getting attributions right is a little involved in this stuff, because I'm not giving quite the original construction of stuff. So I'm going to give where the idea first appeared, and I'm going to write et al. And there's a little bit more about getting the attribute, like correct attributions on the web page or in the notes. So theorem. Where am I? Here. After inverting h, so I'm going to write that as h inverse ckh h of k. I'll say what I mean by inverting h again in a second. Is just chain homotopy equivalent to z adjoin h h inverse squared over z adjoin h inverse. So inverting h, I mean, you just replace copies of z adjoin xh mod x squared minus xh by z adjoin x h inverse. So Laurent polynomials in h mod, the same thing, x squared minus xh. OK. It's important that k is a knot here, so maybe I'll take that as a convention. K is now going to be a knot, and L is going to be a more general link. So some of the things I'll say are going to be specific to knots, and I'll come back and say what's true for links in a minute. Ha, ha, ha. Great. So this is a sort of horrible. Z adjoin H is a complicated ring. This ring, Z adjoin XH or whatever, is sort of a very complicated ring. If I replace Z by a field F, then F adjoin H is not so complicated anymore. That's a PID, principal ideal domain, PID. So this Khovanov homology of K, this H-deformed Khovanov homology of K, is isomorphic to some free part plus some torsion part. So F brackets H plus F brackets H plus T, where this is some torsion part. That's its F brackets H mod P1 of H plus, etc. But plus F brackets H mod Pn of H. And the fact that there are only two of these, there are two summands by this theorem of Lee's. Because each summand, when I invert H, the torsion stuff dies. And I'm left with these, I'm supposed to have two summands, and so I better have had two summands. If I had three, whatever, clear. So theorem Rasmussen et al. The generators of these summands, that is the elements 1 in these summands, lie in quantum gratings differing by 2. So let's say S plus 1 or S minus 1 and S plus 1 for some S.
Robert, this is a real question, but a stupid one. What happened to X in your statement of theorem, of Lee's theorem?
I didn't say anything about X.
So we're ignoring that?
We're ignoring the action of X. Yeah, that's a good question. That's actually not as well understood as you would think. I think I don't know how to upgrade this theorem. Josh is skeptical. Let's punt that till later. We're having dinner anyway. Let's punt it till later. So this element S is S of k. So this is the Rasmussen S invariant. And now everybody is lost, so let me at least give you a couple of examples. Okay, let's give you one example to start. Here, if I, where is the free part? Well, this is definitely going to contribute a free part. This is a Z adjoin H plus a Z adjoin H. And again, multiplication by X takes me from one to the other. But, OK. And then this stuff was all H torsion. That H is sort of killing off the what was going on up there. So what were the quantum gratings? This was in quantum grating 1, and that was in quantum grating 3. So here, the S invariant of this knot, T23, is 1. 2. Good job, Robert. 3 plus 1 over 2 is 2. Right? This is in gratings S minus 1, 2 minus 1, and S plus 1, 2 plus 1. Okay. So if you believe this thing that I sat at home and I computed from this cube, then we got the S invariant of the trefoil. Okay. For the unknot, the S invariant is 0. Exercise. S of unknot is 0. It does not require F to not be characteristic 2. This statement is true in any characteristic. You might also object, this is really SF of k. And the different Fs, different fields actually do give you different invariants here. So at least some of the time. How many different invariants? I think we know that Q, 2, 3, and maybe 5 are different. I don't know that we know beyond that. Yeah. But 2 and 3 and Q are definitely all different. So it's not just that 2 is weird. Maybe I want to move on to the later parts of the talk, 'cause I feel I'm losing the audience. So let me tell you the point here. So theorem, maybe I'll say Khovanov et al. Given a cobordism, I'll draw a picture, sigma from K0 to K1. There's an induced map plus some choices, You get a map from KH, I should have put the 8, well, all right, KHH in grading IJ of K0 to KHH in grading IJ minus chi of sigma of K1. That is, if I have a knot sitting here inside R3, and I've got another knot sitting here inside of R3, let's say this is R3 cross 0 and R3 cross 1. Here's my cobordism sigma. Then I get a map from the Khovanov homology of this end to the Khovanov homology of this end. This is like what continuous maps would do for ordinary homology. These sorts of cobordisms do for, I should have said oriented. Theorem of Rasmussen is that if sigma is connected, the induced map from H inverse KHH H of K0 to H inverse KHH of K1, this was again F brackets H inverse squared, and this is F brackets H inverse squared, is an isomorphism. So this is some non-triviality statement for the map. If you had if you have a connected cobordism, once I invert H so that the homology groups are standard, actually the maps are also standard. Right? And so let me give you the corollary, and I'll even give you the proof of the corollary, and then we'll change topics. The map is, maybe, it's true if the map was based, if the cobordism was based, probably. Yeah, probably. So Josh is proving that what I said is wrong. Although, pass. That sounds very convincing. Everything I've written on the board so far is correct. The discussion, for audience who's not tuned in, the discussion is like, could I have written something stronger on the board? And Josh says yes, of course. And of course, if Josh says it's true, then Josh is right that it's true. But I'm still not willing to put it on the board without having actually thought about it. So, great. Corollary. If K is smoothly sliced, then S of K is 0. Proof. So what was smoothly sliced? Smoothly sliced, here's my knot, was in the boundary of the ball. Sorry, that's not in the boundary of the ball. Here's my knot in the boundary of the ball. And smoothly sliced meant it bounded a smooth disk in the ball. Okay. So just to lead a little ball from that disk, that gives me a cobordism from my knot to the unknot. Okay. So smoothly sliced, I got a cobordism from my knot to the unknot of genus 0. So it's a cylinder from my knot to the unknot. So proof, smoothly slice gives me a cylinder sigma from K to the unknot. So now let's consider, here's my knot. My knot was the trefoil, except that's not sliced, so hopefully it's not quite the trefoil. Here's my knot K, here's the unknot U. This is sigma just done backwards, and then I've got sigma again. OK, and now if I look at KHH, here I've just got F brackets U plus F brackets U. And these are in gradings -1 and 1, because the S invariant for the unknot is 0. So the S invariant is the average of these two gradings, so -1 and 1. Here I've got F brackets U in grading S plus 1, F brackets U in grading S minus 1, and some torsion stuff. And here I've got F brackets U in grading 1, and F brackets U in grading -1. And I've got maps like this. And I know that if I invert H, then the torsion goes away. Right? I invert H, I have an isomorphism. That means that the element, red seems to be my favorite color today. Well, I had that quote at the beginning, right? If I take the element 1 in here, it has to land somewhere in these. It has to have a non-trivial image in this part, because when I invert U, I've got to have a non-zero map. So 1 can't go to 0. Okay, so 1 has to go to something in there. That means that S has to be less than or equal to 0. Okay? This goes something not 0, so this tells me that S is less than 0. So if S is bigger than 0, there's just nowhere it can go that's in grading -1. There's nothing in grading -1 if S is bigger than 0. And on the other hand, if I take, we'll do green for a change. If I take 1 in there, here's my, my Green New Deal, very good. If I take 1 in there, that has to go to something non-zero in these groups. Well, 1 is in grading S minus 1. It tells me S minus 1 has to be bigger than or equal to -1, so S has to be bigger than or equal to 0. So this tells me S is bigger than or equal to 0. And OK, if it's bigger than or equal to 0 and less than or equal to 0, it's 0. It's just because I knew the map has to be non-zero, there's got to be somewhere for these element 1 to go, and you just track. That tells you that S was forced to be 0. Questions? Yes? Exactly the same. Smoothly sliced and smoothly concordant the unknot. That is, having a genus 0 smooth cobordism the unknot are the same thing. And they differ. I mean, you turn one into the other by taking a little ball and cutting it out. Yeah. Good question. More questions?
Can I ask about 2, 3, and Q? So what are those? They're just examples of knots where
They're like random-looking knots where they're different. Yes. The two.
But for torus knots, everything's the same?
For torus knots, everything's, of course, the same, because it's all equal to p minus 1 times q minus 1. Yeah. For any, yeah. I mean, they're all sliced torus invariants.
And is there a broken version of Khovanov homology that works for unoriented cobordisms?
That's a great question. Yeah, so you have board professionals in the audience. So the question was, what about non-orientable cobordisms? And the answer is, Khovanov homology is still functorial. The problem is that the map on this map the localized map is now 0. So this maps into the torsion part. That's similar to the fact that if you have B2 plus bigger than 0, then the map on HF infinity vanishes. So you don't get an S invariant type bound for non-random cobordisms. There is something in that direction in a paper of a former Princeton student, now BP. Yeah, that's right. That's right. Bollinger. Will Bollinger. Yeah. Using some, but it's using some weird constructions. Like I couldn't explain it. Yeah. More questions from the actual audience. That was the end of this section. So we have now a slice obstruction, a smooth slice obstruction. If S of k is not 0, then k is not smoothly sliced. So if delta k of t equals 1, then k is topologically sliced. And if S of k is not 0, then k is not smoothly sliced. So how do I prove that there are knots that are topologically but not smoothly sliced? I don't know. You just find a knot, you compute its Alexander polynomial, and you compute its S invariant, and you see whether you get those two conditions. So I could just draw one and say, just compute, take your favorite computer program and plug it in, and that's the answer. I thought I would give you a family that we can systematically prove both statements for, but I won't give you the proofs. And then that's another topic we can do in future lectures if people want, and we can also not do it if people don't want. So we're in section 2 of the talk. A knot K, given a knot K, and a Seifert surface, that was all of last time, Seifert surface sigma for K, a circle in the interior of sigma that's parallel to the boundary. The boundary is a Seifert longitude for K. And lemma, or exercise, that's what I meant to call it, exercise, that up to isotopy in R3 minus K, the set of Seifert longitudes doesn't depend on the Seifert surface. Is independent of the choice of Seifert surface. And now I would like to give you an example. So I remind you that we had this Seifert surface was like my favorite example last time for the trefoil. Try orange, that'll be different. And so a Seifert longitude is you just take this thing that goes, along the boundary, whatever, that goes parallel to the boundary, along the surface parallel to the boundary. So here's a Seifert longitude. That's not super visible at these crossings because, like, the crossings have turned into quadruple points, right? There are 4 different strands crossing over each other there, so you kind of can't really see what's going on. I mean, you understand what's going on. You take a piece of paper, there's a little twisted strip there, and you drew some curves on it parallel to the boundary. You understand it, it's just you can't really see it. So I took it and I pushed the orange curve a little bit so that you didn't have this quadruple point, and it looks god-awful, but like here's that same orange curve drawn. And for some reason, I thought I would screw this up drawing it in real time, so I drew it ahead of time. Seifert longitude. Nice, simple. So a neighborhood of my naught k is identified with a standard circle cross D2. And I can choose the identification such that the points like S1 cross, I don't know, 0, 1. 0, 1 is a point in D2. So S1 cross 0, 1 is a point, is a circle in here, and so it gives me a circle in there, is a Seifert longitude. This is called the Seifert framing of K, but it's a particular way of identifying a neighborhood with this. This is like a z's worth of identifications, if you think about it. And great. Now, fix a naught P in, let's say, S1 cross D2. I will draw an example. Here is S1 cross D2. This is solid. Right? It's a solid torus. It's an actual bagel. And here is a, I'm absolutely guaranteed to draw the wrong one. It's just hopeless. OK, we'll try. Here is a example of a knot P in S1 cross D2. In S3, this is, you could just untwist this. In S1 cross D2, you sort of obviously can't untwist it. So the image of P in neighborhood of K, thought of sitting inside R3, is the satellite knot with pattern P and companion K. And so I'll draw an example here. Here's that pattern P. I just stick it inside a neighborhood here, so I just do this to this picture. And here is, oh, this is called often P of K. And so this, now that I've joined it up, this is P of K. The word companion used to bother me. I think the word companion comes from thinking about these knots as the motion of celestial bodies. So the Earth is the companion of the moon, is I think the image you're supposed to have in mind. And if you think about the path that the moon traces out, it'll be a satellite knot around the path that the Earth traces out, at least if the moon's orbit closes up. So I think this terminology comes from celestial mechanics. I just made that up. I didn't read it anywhere. Elliot is not happy.
It's complicated.
I believe that. Fine. That's also a good topic for dinner. Maybe a better topic. Keep going, Robert. This one is famous. This is called the Whitehead. This is the hopefully positive Whitehead pattern. And this particular one is WH plus. That stands for positive Whitehead double of the trefoil. So this is the positive Whitehead double. OK, well, that's a nice construction. Why am I telling you this? The Alexander polynomial behaves very simply. Here's a theorem that I didn't look up the attribution. Probably should have. The Alexander polynomial of P of K is the Alexander polynomial of P times the Alexander polynomial of K evaluated at t to the n, where n is the algebraic winding number of P in S1 cross D2. So in this example, this circle goes around twice, but if we trace around it, it goes around twice in opposite directions. I go over that way, and then I come back this way. So its algebraic winding number is 0. So here, n is 0. If I think about that as a knot in S3, it's the unknot, so its Alexander polynomial is 1. So a corollary is that the Alexander polynomial of the Whitehead double of any knot k is 1. So the Whitehead double of k, that was easy. This was just from that theorem. Like half the proof is on the exercises. The whole proof is in Licorice if you want to read it. So the Whitehead double of k is topologically slice. Awesome. No. There's no way to see that the Whitehead double is topologically sliced directly. Because stay tuned for the next theorem. The question was, can you see directly that the Whitehead double is topologically slice? Theorem, I don't know. I'll put some names on. Rudolph, Head and Ording, Shimakovich. The S invariant of the Whitehead double of T2, 3 is 2. More generally, if K is a closure of a positive braid, the S invariant of the Whitehead double of K is 2. So corollary, the Whitehead double of T2, 3 is topologically, but not smoothly slice. I'll philosophize in just a second, but here, open question. Suppose I take the other trefoil, just twist them the opposite direction. If I take the Whitehead double of T minus 2, 3, is that smoothly slice? So this was one of the two famous knots, the smooth slice status of which wasn't known up until about 2020 when Lisa Piccirillo resolved the smooth slice status of the other one. So this is like sort of a famous question. That shows you how delicate this stuff is, because, I mean, again, the other trefoils, reverse all those crossings. Take the mirror image. That's a very similar knot, but then this question's open. Alternatively, take the other clasp here. This is why I was able to answer, not that thing, but the first statement is why I was able to answer no to the question, can I give an explicit proof of this? You can't explicitly find slice disks for non-smoothly sliced knots. At least nobody's ever found one. So if I could answer that question, I would have done something surprising. OK, exotic R4. Three, black box theorems. Theorem A. Maybe I'll say this is Moncrief's 1960 plus stuff. In dimensions less than 4, smooth structures exist. So if M is a manifold, maybe with boundary, is a topological manifold, maybe with boundary, of dimension less than or equal to 3, then M has a smooth structure. And if M and M prime are smooth manifolds of dimension less than or equal to 3, and phi from M to M prime is a homeomorphism, then phi is isotopic to a diffeomorphism. So they exist, and they're unique in a very strong sense. You can take your favorite identification and just move it to being a smooth identification. Okay, so this is a very strong form of uniqueness. A pretty strong form of uniqueness. The second one, the techniques are different from ones I've been giving. There are references on the website. Theorem B. I think the techniques are sort of similar to the Friedman type results that I talked about last time but didn't prove. Any connected, non-compact, 4-manifold, maybe with boundary, has a smooth structure. Okay. So now let me give you an exotic R4. Maybe I'll give it to you, and then I'll give you the main lemma to prove that it's exotic at the end. So no, I can't do that. I need the lemma. So this lemma has become incredibly popular in the last 10 years, called the trace embedding lemma. I'm going to give you 2/4 of it. So let K be a knot. 1, if K is topologically slice, then there's a embedding. Oh, I didn't tell you the notation. You know, you get rushed, you screw things up. Let me give you the notation. So let's let xk0 be d4 union d2 cross d2 along so that I glue where I glue S1 cross d2 to a neighborhood of k such that S1 cross point is a Seifert longitude. So I'll draw a very dimensionally reduced picture. Here's K. This is D4. Well, what you're actually seeing is D2. So I'll put the actual dimensions you're seeing in parentheses. Here is D2 cross D2. And of course, what you're actually seeing is D1 cross D1. And this whole thing is xk0. K is topological slice, then there's an embedding xk0 into, I don't know, R4 or S4, whichever, it's the same, such that, let's call this, say, psi, Psi restricted to the boundary is locally flat. 2, if there is a smooth embedding xk0 into R4 or S4, it doesn't matter, then k is smoothly slice. The proof is not hard. I'll just not say it because we're short about 5 minutes. But this is not a hard thing to prove. And now, so now we have this knot k, which is topologically but not smoothly slice. By the trace embedding lemma, part 1, I can embed xk0 into R4. So here's my R4. And here's my xk0. It's embedded. It's a topologically locally flat embedding. It's not smooth, so it's therefore drawn not smooth. Let's call the complement mk. So mk, this is psi, is R4 minus psi of xk0. MK is kind of horrible. I mean, inside it's just the interior is just an open subset of R4, but the boundary is some non-smooth thing. By theorem B, this is the Quinn theorem, MK has a smooth structure. And by theorem A, psi restricted to the boundary of xk0. So this is a map from the boundary of xk0 to the boundary of mk is isotopic to a diffeomorphism. Let's call that something else. How about phi? Let R be xk0 glued by phi to mk. R is homeo but not diffeo to R4. And now I have about 30 seconds left, so I'll just prove that for you in the air, but that's really enough, and anyway, being recorded. Homeomorphic, if I'd glued back using psi, I would have just gotten R4 back. I deleted something, and then I put it back in exactly the same way. If I glue by phi, since that's isotopic to psi, I get a homeomorphic manifold. That's on the homework. That's easy. Okay. It uses locally flat on the boundary thing, but other than that, that's easy. Okay, so they're homeomorphic to R4 because I just glued by 2 different isotopic homeomorphisms. But now it's smooth. Why is not diffeomorphic to R4? Well, xk0 is sitting smoothly inside here, and the trace embedding theorem says it can't sit smoothly inside R4 if k isn't slice. Case, that was part 2 of the trace embedding theorem, trace embedding lemma. So there's your exotic R4. Was that entirely satisfying? No, that was not entirely satisfying because it can't be. We don't have an actually explicit construction of these things, but such is life. I remind you, the Google form will determine what happens in the next 4 lectures. We'll either jump to some more recent stuff, or we'll fill in some parts of today, or we'll talk about invariance of surfaces, which is something that I was going to skip, but that we could, Khovanov invariance of surfaces we could talk about. Depends on interest, or we'll do something else. There's a box if you want to request something else. I will probably ignore your requests, but I'll read them, and I'll probably decide they were a bad idea. But if they're a good idea, I will absolutely do them. OK, thanks very much. See you next time.